Okay, so last time we did Markovnikov's rule, very important. Okay, if you missed that lecture, make sure you see that on the video. Very, very important. Okay? So you may be lost today as a result. If you weren't here, we'll try to get you caught up to speed. Okay? So what we're going to do now is an alkene reaction with HBr and a peroxide. HBr and peroxide. Okay? So let's do an example of this. Let's take, for example, this alkene here. If you note here, HBr, then this thing here is a peroxide. Okay, what's the definition of a peroxide? It's something that has a oxygen single bond. Okay, so the one that we drew up there is called hydrogen peroxide because we got hydrogens on both sides. And this peroxide bond turns out to be a very weak bond. Okay? A very weak bond. That'll be the key as we look at this reaction. Okay? But before we look at the mechanism, let's just go ahead and draw the product. The product that we get is this here, where the bromine has gone on the less substituted carbon of the double bond. The bromine has gone on this carbon, not this carbon. If it had gone on this carbon, that'd be called, remember, Markovnikov product. But since it went on the less substituted carbon, we call that the non-Markovnikov product. Okay? That's what this chapter will look at, are Markovnikov and non-Markovnikov products. And we'll see how these form. Okay? But that's the clue you want to remember here. And the key is the use of this peroxide. Okay? So let's look at the mechanism and see how the peroxide is causing this kind of product to form. Okay? So what it is that it is a radical mechanism. Okay? In fact, for future use, that anytime you see a peroxide involved in a reaction, it always involves radicals. You might say, why is that? Well, if you look at the peroxide, remember I said that the oxygen-oxygen bond is very weak. It's such a weak bond that some heat can break it down. So heat can break that down. So this bond actually does a homolytic cleavage where it breaks in two. And so we get two of these hydroxide radicals forming. Okay? That's what happens in hydrogen peroxide. That's why you store it in a brown bottle in cool temperatures if you buy it at the store. You never store it in the oven. Okay? You never store it outside in the sun because it would break down. Okay? When you put it in your mouth, it fizzes. Those bonds are breaking in your mouth and cleaning and everything. Okay? So you may want to clean out your mouth sometime with some peroxide.
So that's why you couldn't, what was the purpose for them putting in the brown bottle?
Protects it from the sun,
Okay.
so it doesn't do that. Okay? So what happens next? Well, after this, let's use one of these hydroxide radicals, and it reacts with HBr. Well, what happens here is a hydrogen abstraction. So the OH dot takes that hydrogen to become water. But the important thing that we get from this is what's left over, and that is the bromine radical. So this bromine radical forms, and this thing here now reacts with our alkene. Okay. So this is the big thing that we were looking for. So let's react it with the alkene over here. Okay, so there's the alkene and the bromine radical. Remember that I said when you see a double bond, you draw in a gigantic set of lone pair on it. Okay. So we're going to react this lone pair with this radical. How's it going to react? Well, this is something new for us. What happens is this bromine joins with that electron to form a bond, and this electron stays on that carbon. So if we draw the result of that, we would end up getting that there. Okay.
Yeah.
So that radical forms. Then that radical reacts with HBr, does a hydrogen abstraction, to give us our product like that. And if you look, we form the bromine radical that can then come back and react with another alkene to give us that, to do this. And so we get what? A chain reaction or propagation. So A and B can repeat. Okay. So this is a new propagation step for us. Okay. But you can see what dominates the bromine adding on the less substituted carbon is the radical. Say, what do you mean by that? Well, let me erase part B here. And let's suppose that the bromine added on that carbon if it added on this carbon, then that other carbon would get the radical. What kind of radical would that be? That's a primary radical, and this one is a secondary radical. Which radical is more stable? Secondary. Okay, so that's why the reaction goes like this. The bromine adds here because they get a more stable radical form. And that's what is dictating the non-Markovnikov, the bromine adding to the less substituted carbon of the double bond. Okay, so it all has to deal with radical stability. Okay. Last time, if you remember in class, for those that were here, we took and did, say, a reaction like that, where I did not have peroxide, and the bromine went on the more substituted carbon of the double bond. Remember that? And so this was the Markovnikov product. Okay. Remember why that went on there? Because this dealt with carbocation intermediates, but this deals with radical intermediates. Okay? So because you have two different mechanisms, that's what dictates this product versus that product. So if you see peroxide, if you don't see any peroxide, you get the regular Markovnikov as your major product. Okay? Again, if you weren't here last time, make sure you watch that video. Any questions on that? Okay? So kind of long and complicated, just to prove or show why this particular product here forms. Okay. Well, let's go on to another reaction. Let's look at this one. Let's take an alkene plus H3O plus, the hydronium ion. Okay. What this is going to give us is a Markovnikov alcohol. Remember what an alcohol is? What does it have in the molecule? NOH. Okay. So let's take a look at an example. Let's just stick with our friend here. And react with H3O plus. Okay. The hydronium ion. Remember when we looked at H3O plus we have a positive charge on the oxygen. Remember what we said that makes these hydrogens? What property? When you see hydrogens on an oxygen with a positive charge, what property do those hydrogens have? They are what? Starts with an A. Acidic. Okay? So all these hydrogens are acidic. And remember, the alkene acts as what? A base. So what do you think the pi electrons are going to attack there? What do you think they're going to attack? One of the hydrogens. Okay? Try to make that an easy question. Some of you didn't want to answer. Why not? Okay. So here's the mechanism. Pi electrons attack acidic hydrogen. Could have attacked any of the three. Then those electrons dump into the positive oxygen. That's electron deficient. Okay. So remember from last time, when it attacks an electrophile, acidic hydrogens or electrophilic hydrogens, that the hydrogen could go on either carbon. So if it goes on this carbon, that carbon gets the positive charge. Or if it went on that carbon, then that carbon got the positive charge. Okay? Which was the more stable one? The first one. So now water has formed here, so let's bring it in. So it'll attack the positive charge. Let's add the water on. Like that. And I just won't show this hydrogen, I'll just coalesce it in there. So this carbon here is what, a CH3. Okay. So the water has added on. Well, oxygen now has what on it? Positive charge. What do we say about it if it has a positive charge? The hydrogens on it are acidic, okay? Just like up here. It's the same thing. So what do you think we're going to do now? I hope you're not using a cell phone. You could please put it away. Okay, since these are acidic, what will remove it? Starts with a B, a base. Well, let's bring in another water molecule. So the water can now take an acidic hydrogen. finally formed are Markovnikov alcohol. Okay. So you want to be familiar with this mechanism. There's a few steps to it. Okay.
I got a question. So basically, you keep adding water until you get to alcohol?
Right. Okay, so the first step takes an acidic or electrophilic hydrogen, creates the carbocation. I'll choose the more stable carbocation. Water acts on it, then takes acidic hydrogen and get the alcohol. Water here is acting as what? A nucleophile. Remember why we said it's acting as a nucleophile? Because it's attacking what? What's it attacking?
A carbon.
A carbon. But down here, it's acting as a base. Because why? It's attacking a hydrogen. Okay? So it's doing the same thing in both cases. It's just attacking a different thing. Okay?
Dr. Miller,
Yeah.
is this one like a continuation type reaction? Because it doesn't give you back an H3, OH3?
Yeah, it gives, yeah, so form it back again. Okay, but I'm only concerned about this product here. Okay. All right. Any other questions on it? So make sure you're familiar with this mechanism. Okay? Now something can act as a nucleophile and a base, just in terms of what it's being related to. Okay? Just like, for example, if you're a guy, you could be a dad or you could be a son, all in relation to who you're talking about. Okay? But you're still the same thing. Okay? Just like the water remains the same. All right, any questions on that there? All right, let's look at another way to make an alcohol. This is what's called an oxymercuration reaction. Okay. So what are we going to do here? Well, here's the setup. We'll take an alkene. And we're going to react it with two different reagents. And we're going to form alcohol that is Markovnikov once again. What does Markovnikov alcohol mean? The OH is on what? The more substituted carbon of the alcohol. Okay? Make sure you know what I'm talking about. Well, what are the reagents this time? Okay? Last time we did H3O plus. This time we're going to use these reagents. Okay? So in the first step, we use this HG OHC taken twice. This stands for mercuric acetate. Okay. And it has this acetate, this thing here. Okay, so we just condense it down to OAC, making it easier to write. Okay, so we combine it in water. Then the second step, we use NaBH4, which is called sodium borohydride. Okay. So let's take a look at an example. And what we'll get is the Markovnikov alcohol, like that. Okay. Any questions on it? Okay. One key thing you want to keep your eye on is what is here after that comma. Note we have water. Okay. Because sometimes you'll see that being different. Instead of water, you might have an alcohol. Well, when you change this up to an alcohol, now what you're going to get is this adding on instead of the water having added on. So you get OCH3 on there instead. Question?
So it all depends on what comes after the
That's
mercuric
right.
acetate?
What comes after the acetate? So if you see water, OH, if you see an alcohol, add it on. It's that easy. Okay. Let me give you one, see if you can do it. See if you can draw the product for that one. What'd you get back?
Good. Well, I had to draw it.
Okay. How many people got that one? Couple. Any questions on that? Okay, so you look to the right. Here, this time it's a 2-carbon alcohol. So CH3, CH2O adds to the more substituted carbon of the double bond. And so we get that. Okay? Just like up here, just a different alcohol, that added to the more substituted carbon of the double bond. Okay? If it was water, then I would have put what? OH here.
Always drop on hydrogen.
Always drop behind. Any other questions? Any other questions? All right, let's look at one more reaction, and we'll call it a day. Okay, this one here we'll call this the hydroboration reaction.
Excuse me, one question real quick before you move on. You also on the list have demercuration, is that gonna be something we need to focus on as well?
Yeah, that's all encapsulated. So the hydroboration, what are we doing here? Taking the alkene, again, we're going to do a 2-step reaction. And our product here, again, will be an alcohol. But this time, it'll be a non-Markovnikov alcohol. So what's that going to mean? The OH will be where?
On the less substitute.
On the less substituted carbon of the double bond. Okay? So, have a new set of reagents. BH3, H2O2, and OH minus. Okay. BH3, it's often called borane. Okay. So let's take a look at an example of this. So here, as soon as you see the ingredients, you see the boron, okay? So that means hydroboration, okay? That should be a tip-off, okay? Alcohol, non-Markovnikov. So this time the OH will go on this carbon. Okay? So we get non-Markov carbon. Okay? So that's what we want to be able to do in organic chemistry. Okay? I want to be able to have the ability to put a group here or here. Okay? And I just have different reagents to do that. Okay? Again, I'm not going to hold you accountable for the mechanism, but just be able to know how to draw the product here. Okay? One thing about this, sometimes you'll see in the book that being attached to THF, okay, which is just a solvent. So it doesn't have anything to do with the reaction, but sometimes you'll see that in your homework problems. Don't let that throw you off. Okay? So suppose I gave you that reaction, can you draw the product for that one? Okay, so if you did it right, should have got that right. I maybe got that right. Okay, let's see if I can catch it. Okay, so any questions as we finish up here? Yeah.
Is that hydroboration always gonna have those, BH3 and H2O2 and OH?
Yeah.
That's always gonna be the case?
That's right.
Okay.
So that'll be your tip-off. So let's see that, okay. Alcohol, non-Markov coffee. Okay, so always let your ingredients here direct you, okay? So be putting these on flashcards and drill yourself, okay? Because when this next exam comes up, you're gonna have a whole sheet of reactions. And if you don't know those reactions, you're gonna miss a lot of points. Okay? If you have them down, those should be very easy points. Okay? We'll see you on Monday. Don't forget your quizzes up there.